Welcome to the video on integration by substitution. Integration by substitution is a method which we can use to solve more complex integrals. By using this small trick, we will simplify the more complex integral into an integral which we know how to solve. In this video, I will show you what integration by substitution, the method, is all about, and I will also show a few examples where we use this method. If we look at the integral which we would like to solve as f of g of x times g dashed x dx, it looks rather complex. But let's see what will happen if we substitute gx to be equal to t. The reason for us doing that is because that is part of the small trick which will finally make this more complex integral easier for us to solve. Because if gx is equal to t and we differentiate that for x, that is g dashed x must be equal to dt dx, and we multiply on both sides with dx, we get that dt is equal to g dashed x dx. And that we recognize as something which we have seen before. G dashed x dx is exactly what we have up here, and that is equal to dt. So if we insert this knowledge that we have from down here, that gx is equal to t up to our original given assignment up here, we see that the integral of f of t as gx is equal to t times g dashed x dx, which is exactly equal to dt, we get a much more simple integral to look at. Integrating ft for ft dt will then be equal to capital F of t added with our integration constant. And since t is equal to gx, that will also be equal to f capital F gx plus c. So this original given assignment, which looks quite complex, by substituting dx to be equal to t, we end up with something which is much more simple for us to solve. As always with integration, we can check our result which we come up with here by differentiating the result, and then hopefully we will get what we have in the original given assignment up here. So let's try to do that. We'll do it down here. To check whether if I differentiate what I have here, so that will be ddx of f gx, and of course I leave out the integration constant, as this one differentiated will be eliminated, equal to 0, as you know. Then we see that we have a composite function here. The internal function is gx and the external function is capital F. So we need to use the chain rule to differentiate what we have here. So that is, we differentiate the external, leave the internal as it is, and then we multiply that with the internal differentiated, according to the chain rule. And the capital F function differentiated must be equal to the function f, so f of dx times g dashed x, which luckily is also what we have up here. So when we differentiate our result, the check which we can always do when we integrate, we should get the original given assignment which we have up here, f gx times g dashed x. So we see that we haven't done anything wrong here, so that's fine. Okay, so let us look into one example where we use the integration by substitution. Then it probably will make a bit more sense to look at. The example which I have chosen to include here is the exercise where we should integrate square root 3x squared plus 1 times 6x dx. So again, an exercise here which looks quite complicated to integrate, but if we use our method of substitution, we will soon see that it's quite simple to approach. So we have to substitute what here is our internal function. Here it's what we find below the square root sign, t to be equal to 3x squared plus 1. And then we differentiate that for x, so it's dt dx will be equal to, that must be 6x. The 1 will be eliminated when we differentiate, and then we multiply with dx on both sides, so we get dt equals 6x dx. So we see here that dt, which is equal to 6x dx, is exactly what you have up here in the original given assignment. So therefore, if we substitute t to be equal to 3x squared plus 1, we get the square root of t times 6x dx, which is exactly equal to dt. So by using the method of substitution, this quite complex assignment to start with end up with a much easier assignment to approach. We remember that the square root of t is the same as the power of 1/2. And that one is one of the simple integrals which we know how to solve. So that is equal to 2/3 t to the power of 3/2 plus c. So now we just need to substitute back that t is equal to 3x squared plus 1 to end up with the final result to the given assignment here. So 2/3 times 3x squared plus 1 to the power of 3/2 plus c. That's the result to the given assignment. Alright, as always we can check our result by finding the first derivative here, and hopefully we'll end up with what we have given up here in the original assignment. So let's try to see if that's the case. Do a small check here by differentiating the result. For x, and again we leave out the integration constant as that one will be eliminated when we differentiate. So how we differentiate this composite function is, first of all, we differentiate the external function, so we move down the exponent in front. So that will be 3/2. We leave the internal function as it is, according to the chain rule. And then we have to subtract 1 to our exponent, so that will be equal to 1/2. And then we finally need to multiply that with the internal function differentiated. 3x squared plus 1 differentiated is 6x. Alright, so we just need to look at this simplified a bit. 2/3 times 3/2 eliminate each other. To the power of 1/2 is the same as the square root 3x squared plus 1. Multiply that with 6x. So our check is completed. When we differentiate this result, which we have here, we get our original given assignment. So that's correct what we have done. So that was one example of how you can use the method of substitution to integrate much more complex assignments as you have done so far. In this first example, we saw that dt was exactly equal to 6x dx, which was what was given here in the assignment. But that is not always the case, but that's no problem, as we just have to do a small operation to overcome this. Let's look at a new example to see how we do that. In the second example here I've chosen to bring along, we should try to solve the integral of x squared divided by 3x to the power 3 minus 1 all to the power 4 dx. So again, a quite complex integral, but by using the method of substitution we could make it simple and be able to solve it. So we need to substitute again our internal function. Here it will be t equals 3x to the power of 3 minus 1. We differentiate that for x, so dt dx must be equal to 9x squared. Then we see here that if we multiply with dx on both sides, we get 9x squared dx, but we only have x squared dx in our original given assignment. But that's no problem, because if we at the same time just divide with 9 on both sides, we see that 1/9 dt must be equal to x squared dx. So when we substitute into the assignment up here, we see that it's 1/9 dt, which is equal to x squared dx. So that we just have to insert into our assignment here. So let's see. We had just agreed that t is equal to 3x to the power of 3 minus 1. That's what we have here in denominator, to the power of 4. And x squared dx equals 1/9 dt, like that. So the constant here, we just, like always, move outside the integration sign. So that is 1/9 integral of t to the power of -4. I just rewrite this into, because now I have the assignment given into a simple one, which we know how to solve. I'll just make a line here so we don't mix it up. So let's do that. The integral of t to the power of -4, that must be equal to t to the power, and we add 1 to the exponent, and then it must be multiplied that with -1/3, added with the integration constant. So altogether it must be equal to -1/27 times, and t, which is equal to 3x to the power of 3 minus 1 to the power of -3 plus c. If you want to, you can rewrite this into a positive power by putting it into the denominator, so we could do that. So that will be equal to -1 divided by 27 times 3x to the power of 3 minus 1 to the power of a positive 3, added with the integration constant c. So that is the result to the original given assignment from up here. As always, you can check your result by finding the first derivative of what you have figured out, of the result you figured out here, and that should hopefully be equal to the original given assignment. Then you know that you're on track. I think you can do that on your own using the chain rule, just as I showed in the first example. So that is what integration by substitution is all about. We can use it when we have more complex integrals, like the ones which are stated up here in a general form. We use it by substituting this internal function dx to be equal to t, and then we finally end up with a more simple integral which we can solve, and we substitute back again t to be equal to gx at the final end before we have our final result. And remember that you can always check your result by using differentiation to the result given. So finding the first derivative of the result you have figured out will lead you to the original given integral, otherwise you have done something wrong. So that's what integration by substitution is all about. Thank you for listening.